Metamaterials, well, they're not something you'd stumble upon in nature. They're these fascinating, artificially engineered structures. You see, their properties don't just depend on the materials they're made of, but rather from their unique design. Scientists, with all their precision, arrange tiny components that are smaller than the wavelength of light or other waves they aim to control. It's this meticulous arrangement that grants them extraordinary abilities. For instance, some of these metamaterials can bend light in ways that are quite unusual. This has led to some pretty exciting ideas like invisibility cloaks, which once seemed like something straight out of science fiction. These materials really represent a major shift in how we think about and control waves, opening up new possibilities for technology that were, well, previously unimaginable. The journey into metamaterials began with a simple idea. We wanted to create materials with properties that don't exist naturally. Imagine properties like a negative refractive index. This means light bends in the opposite direction compared to how it bends in water or glass. Early designs used small metallic rings and wires. These structures could manipulate electromagnetic waves in very specific pre-programmed ways. The real breakthrough was realizing that the collective behavior of these tiny structures, these meta-atoms, was more important than the properties of the base materials themselves. This concept has since expanded beyond light to include sound, heat, and even seismic waves. The power of these materials lies in their tunability. By changing the shape, size, or spacing of their internal structures, we can fine-tune their response to waves. This is a fundamental difference from natural materials, which have fixed properties. Initially, these metamaterials were linear. This means their response was directly proportional to the strength of the incoming wave. If you doubled the intensity of the light, the material's response would also double. While useful, this linear behavior had its limits. Scientists soon began to wonder what would happen if the response was not so simple, leading to the development of a new, more dynamic class of materials. The next evolutionary step was to introduce nonlinearity. Nonlinear metamaterials have properties that change depending on the intensity of the incoming wave. This is a crucial feature. It allows the material to actively interact with and modify the waves passing through it. For example, a nonlinear material could change its refractive index in response to a powerful laser beam. This opened the door to a whole new world of applications. We could now think about creating all optical switches, frequency converters, and sensors with unprecedented sensitivity. The focus shifted from passively guiding waves to actively controlling them in real time, marking a new era in materials science. One of the most direct ways to create nonlinear metamaterials is to insert nonlinear elements into their structure. Imagine our array of tiny metallic rings. We can place a very small nonlinear component, like a diode, into the gap of each ring. Diodes are electronic components whose electrical resistance changes with the voltage applied to them. When an electromagnetic wave hits the metamaterial, it creates a voltage across the diode. If the wave is strong enough, the diode's properties change, which in turn alters the entire metamaterial's response. This method is very practical, especially for controlling microwaves, and allows for dynamic, real-time tuning of the material's function. Another clever approach involves using a nonlinear host medium. Instead of adding separate components, we can embed the metamaterial's metallic or dielectric structures within a material that is already intrinsically nonlinear. For example, certain types of glass and crystals change their refractive index when exposed to intense light. By placing our meta-atoms inside such a medium, the strong electric fields generated around the structures can trigger the nonlinearity of the surrounding host material. This technique is particularly effective for optical frequencies. It allows the unique field-shaping properties of the metamaterial to work together with the inherent nonlinearity of the host, creating a powerful synergistic effect for controlling light. Local field enhancement is a key principle that makes many nonlinear metamaterials work so well. The metallic components of a metamaterial, like split-ring resonators or nanoantennas, are designed to capture and concentrate electromagnetic energy into very small spaces. This creates hotspots where the electric field is many times stronger than the incoming wave. If we place a nonlinear material in these hotspots, its nonlinear effects are magnified dramatically. This means we can trigger a strong nonlinear response with a much weaker input signal. This enhancement is crucial for making practical devices that do not require extremely high-power lasers to operate. We can also build nonlinearity directly into the structure of the metamaterial itself. This is known as intrinsic structural nonlinearity. Instead of relying on added components or special host materials, the geometry of the structure is designed to change in response to a strong field. For instance, a flexible metamaterial might have tiny parts that physically move or deform when hit by a powerful wave. This physical change alters the geometry and, consequently, the electromagnetic properties of the material. This approach offers a robust way to achieve nonlinearity, as it is built into the very fabric of the material, potentially leading to more durable and integrated devices. Nonlinear transmission lines are another important platform for studying and implementing nonlinear metamaterial concepts. A transmission line is simply a structure that guides waves, like a coaxial cable. We can create a nonlinear version by periodically loading a standard transmission line with nonlinear elements, such as varactor diodes. Each segment of the line acts like a meta-atom. The resulting structure behaves as a one-dimensional metamaterial that can be used to manipulate electrical signals in fascinating ways. These nonlinear transmission lines are excellent for applications like pulse shaping, frequency generation, and creating specialized wave phenomena like solitons, which are self-reinforcing solitary waves that maintain their shape while they travel. The design of nonlinear metamaterials has become increasingly sophisticated, moving beyond simple rings and wires. Today, we use complex three-dimensional architectures. Advanced manufacturing techniques like three-dimensional printing, electron beam lithography, and self-assembly allow us to build intricate structures with nanoscale precision. These methods enable the creation of metamaterials with tailored, nonlinear responses across the entire electromagnetic spectrum, from radio waves to visible light. For example, we can design structures that efficiently convert low-frequency light into high-frequency light, a process known as harmonic generation. This is vital for developing new light sources and imaging systems that operate at frequencies where conventional lasers are not available. The choice of materials is just as important as the structure. While metals have been popular for their ability to confine fields, they also suffer from energy loss, especially at optical frequencies. This has driven research into all dielectric metamaterials. These are made from materials like silicon or titanium dioxide, which have low loss and high refractive indices. By carefully shaping these dielectric materials into nanoparticles or other resonant structures, we can achieve strong field enhancement and significant nonlinear effects without the inherent losses of metals. This has paved the way for highly efficient nonlinear devices, such as metasurfaces that can sculpt the wavefront of light in a nonlinear fashion. Furthermore, the field is expanding to embrace hybrid approaches. We can combine different types of nonlinearity within a single metamaterial to achieve new functionalities. For example, a material could have both an electronic nonlinearity from an inserted diode and a thermal nonlinearity, where its properties change with temperature. By controlling the input signal, we could selectively activate one type of nonlinearity over the other. This multi-physics approach adds another layer of control and programmability, allowing us to design smart metamaterials that can adapt their function in response to multiple environmental stimuli, not just the intensity of a single wave. This integration promises more versatile and intelligent systems for wave manipulation. The frontier of nonlinear metamaterials is now merging with the quantum world. Researchers are exploring how to incorporate quantum elements, such as quantum dots or superconducting circuits, into metamaterial designs. Quantum dots are tiny semiconductor crystals that behave like artificial atoms with distinct energy levels. When integrated into a metamaterial, they can provide an extremely strong and controllable nonlinear response, even at the level of single photons. This opens the door to quantum metamaterials, which could be used to build components for quantum computing and quantum communication networks, enabling secure information transfer and ultra-powerful computation based on the laws of quantum mechanics. Superconducting elements are also bringing revolutionary changes. When cooled to very low temperatures, superconductors have zero electrical resistance, meaning they are extremely low loss. By making metamaterial components out of superconductors, we can create resonators with incredibly high quality factors. This means they can store energy for a very long time, leading to massive field enhancement. Furthermore, superconducting devices like Josephson junctions have a naturally strong and tunable nonlinearity. A metamaterial made with these junctions can be tuned with an external magnetic field, providing a fast and efficient way to control its properties. This technology is highly promising for creating ultra-sensitive detectors and low-noise amplifiers for radio astronomy and quantum measurements. Looking forward, the potential of nonlinear metamaterials seems almost limitless. They are poised to transform numerous fields. In telecommunications, they could lead to all optical routers that process data at the speed of light, breaking current electronic bottlenecks. In medicine, they could enable new imaging techniques with higher resolution or be used in targeted therapies where nonlinear effects are activated only at a specific location in the body. For energy, they could improve the efficiency of solar cells by trapping light more effectively or by converting unusable parts of the solar spectrum into electricity. The ability to actively control waves with such precision is a game-changer for countless applications. In summary, nonlinear metamaterials represent a powerful paradigm shift in materials science and engineering. By moving beyond the static, linear properties of conventional materials, we have unlocked the ability to dynamically control and shape waves with unprecedented freedom. From simple diode-loaded structures to complex quantum and superconducting systems, the methods for creating these materials are becoming more sophisticated every day. The journey is far from over. As we continue to explore new designs, materials, and physical principles, nonlinear metamaterials will undoubtedly continue to drive innovation and enable technologies that we are only just beginning to imagine, shaping the future of how we interact with the world around us.